Instead of a thin rod, we're going to have a thin plate, like sheet metal. And let's make this plate shaped like a semicircle, say like this. And to keep things simple, though not too simple, we are going to assume this plate has a constant density, delta, that's not a function of x. A constant, you could call it an area density in like grams per square centimeter, for example. The thing that's going to require calculus here is the fact that this thin plate, this thin sheet, lamina is actually the more official name. This lamina is not a rectangle shape. It's a semicircle. That's what's going to require us to use calculus. Though it does have some symmetry to it. Again, I'm ultimately after the center of mass. If I imagine taking this thin plate and turning it so the thinness is this way, where could I put a little, like a pencil, to make it balance? That would be the center of mass. Because of the constant area density, if I create a coordinate system like this, by symmetry, the center of mass is going to be on the y-axis. If I call the coordinates of the center of mass x bar comma y bar, the x coordinate is going to be 0 by symmetry. And I only have to figure out the y coordinate. But that begs the question, how do I do that? Get out your scissors or your knife. Start slicing this up. How? Since it's the y bar that I got to figure it out, I should slice it perpendicular to the y-axis with thin slices like this. Say that distance is y. Say this length right there is delta y. And effectively, figure out the small mass of this thin slice. Imagine all that mass is on the y-axis. Its moment will be its mass times y itself. Add those up to get the total moment. Convert to an integral to find it more precisely. Divide by the total mass to find y bar, the center of mass in the y direction. So how do I find what would be useful here? How do I find, I want to find the small mass of this thin slice. Probably we need to think of this as being an approximate rectangle right there and find this length first, right? What should I call it? Should I go back to L? L of y is not a thin rod anymore, though. Oh, well, I mean, you could pretend the thin slice is like a thin rod, but the entire thing is not a thin rod. Actually, the book calls this A of y instead of L of y because they're thinking more generally in terms of three-dimensional objects. And instead of a cross-sectional length, they're thinking cross-sectional areas. So the book calls this A of y in the reading, but it is a length. What does it equal? Well, I need to know what the semicircle is. Let's say this is 3, 3, and -3 here. So the radius is 3. The equation of the circle here would be x squared plus y squared is 3 squared, 9. So y, well, okay, x, the horizontal distance right there, is going to be square root of 9 minus y squared. And L, as a function of y, will be 2 times that, because it's twice as long. This distance right there is the square root for a given value of y. That distance is the first coordinate of that point, which is what you get when you solve for x as a function of y here. You got to double it to get the entire length. So hang on here, we're almost done, at least in terms of setting it up. The approximate mass of that thin slice would be L of y times delta y, or that, no, that's the approximate area, sorry. delta A is L of y times delta y. The approximate mass of that would be that area in square centimeters times the constant density, delta times delta A. Keep in mind here again, though, that delta is a constant, a number, like 5 or something. What about the moment, the small moment of that thin slice? It would be delta M times Y. Put all this together, it would be delta times Y times L of Y times delta Y. The total moment is going to be a sum of little moments, approximately a sum of these things. We're getting closer to the integral here. Ultimately, this is the function that you're going to integrate. The total moment is going to be the integral of delta times y times L of y dy from what to what? In this problem, it would be 0 to 3. Y goes from 0 to 3. I'd replace L of y with 2 times square root of 9 minus y squared and do that integral. Is that a hard integral to do? Not as hard as it looks. Keep in mind delta is a constant. Of course, 2 is a constant. That's a times 2 in there. To do the integral, you could do a pretty simple substitution, actually. You could do w equals 9 minus y squared. That would give you that's the moment. To find y bar, then you'd have to take that moment and divide by the total mass. And the total mass would be the area of the semicircle times the density. And the area of the semicircle is 1/2 pi r squared. Multiply that times the density. This would be delta times 1/2 pi r squared. R is 3. So it'd be 9 pi over 2 times delta is going to be what the mass is in this case, and that would help you figure out y bar. Okay? This integral is not as hard as it looks. It could be done. All right. Have a good day.